energy, or without having to use the kinematic formulas, we can use the kinetic energy concept. I got one more example for you. Oh, before I go too far here, if we use this concept, here, so work is equal to F dot D, which is FD cosine theta. The theta we're interested in is the theta you get when the two vectors are arranged so they are tail to tail. So look what this looks like. The D vector in this case is to the right. Where the force vector in this case is to the left. And in our problem it was the frictional force. So I look and I want to know, well, what's the angle between them? Isn't that angle 180 degrees? So if I put this in here, what's the cosine of 180? Well, the cosine of 180 is -1. So this would be equal to, which is the same thing that we have here. So applying this work concept here, the dot product between these two, we end up with the same result if we do it conceptually. Let's take our example one last time. To make it easy, we'll say it starts from rest. Speeds up over time to some speed vi. It does it in some distance. But this time we're going to make it a little more interesting. We're going to say that it's sliding with friction, with coefficient of friction mu, and it's being pulled by some force F. So it's still speeding up, which means that the force to the right has to be bigger than the frictional force, no problem. But how do we express the work done this time? Okay? Well, let's draw the force diagram for it when it's moving this way. Earth is pulling it down, that's the mg. The surface is pushing up, that's the normal. We have some large applied force F to the right, and we have some small force to the left, that's the normal force. So how are we going to express the work done this time? There's two ways to conceptualize it. Let me show you both real fast. So here's our FD graph. One way to think about this is that we can just plot this on here. We know that the force that's applied drags at a distance d. But what do we have in the backward direction? Don't we have some frictional force backward? And we know it's less. And we know it's negative. And so when I look at this like this, I know that my work done is the area here, so if I drop this down, That's the work done by the force. So I'm going to call this WF, the work done by the force. This that's the work done by the friction. And we notice by looking at this, this one is under here, under the axis. This one is above the axis. So this is actually a negative work value. This is a positive work value. So we say the net work, we say the net work must be equal to the work done by the applied force minus the work done by the friction. That's one concept. Okay? That's one concept. Another way to visualize this would be to think about it like this. We already have the net force concept, so how would I think about the net force here? Well, the net force here would be this force minus the applied force minus the frictional force. So what if I just did it that way? So another way to conceptualize it is to think about the net work done is equal to the net force times the distance through which the object moves while the forces are being applied. What I like about this is if there was no friction, right? If there was no friction, you get all this work here, and so you would have a large change in kinetic energy. But if you think about it this way, so you have some large change in kinetic energy here, it would be slowing it down. It would actually be a decrease in kinetic energy. So you have some negative change in the kinetic energy. And obviously, with friction, you'd have less total change in kinetic energy than you did without the friction. So it kind of makes some sense the way that this picture looks and how it's related to this picture. The last concept we want to talk about is called power. So power is a physics concept that's related to work and energy in terms of the fact that we use capital P for power. So here's our general concept. We say that the power is the change in energy divided by the time over which the energy changed. There's a couple different ways to express this. One way to think about this is our change in energy, that is our work. So oftentimes you'll see power is equal to the work divided by the time. You see that often. There's two kinds of power that we can conceptualize. One is called the average power. So if I get the average, basically we're taking the change in the work. So all the work that's done divided by the time. But we don't know how it happens here or there. But it's the average amount. And so we say that the average power is the work divided by the time. There's also the instantaneous. The instantaneous power, for you calculus fans out there, is the dw dt, which it's still the time rate of change, but instead of over a long span, it's the instantaneous, which means your time is right so small. I want to know what is the power at this instant in time. This tells you what the average power is over this long span of time, which we call the delta t. So those are the differences between these two. And let's see how it manifests. One way is you can just calculate the work, divide by the time, and you're good to go. But there's another way that we see this also. There's another way we see this also, which is actually kind of interesting. If we think about the instantaneous. One of the things we talk about when we talk about work is the force applied times the distance that it goes. And so if we think about the instantaneous power, so it's the change in the force distance product divided by the time. But let's say the force is constant, so if the force is constant, it stays out front. So what this is talking about the force times the change in the distance divided by the change in time. But look what this looks like. If I look at the way this looks, it looks like I have the change in distance divided by the change in time. Well, the distance divided by time, that's the velocity. And so when I look with this, if the change in distance divided by the change in time is the velocity, then another concept for power, another concept for instantaneous power is the force-velocity product.